So last time we talked about polar coordinates. We took a look at some graphs of polar coordinates, and hopefully you got comfortable in being able to graph polar coordinates on your graphing calculators. And we looked at some families. We looked at some flower petals and hearts with holes in them. And there are many other types of graphs that we didn't look at. And so when you do more of those homework problems, you'll get to see a little bit more types of or families of these polar coordinate graphs. I guess one of the other things that I did want to show you was but another interesting polar coordinate graph. I wouldn't necessarily call this a family, I guess, but you can think about it if you look at polynomials, generally how they might look like. So for something like theta, as our simple example, if you put r equals to theta, imagine that stick going around in a circle and the angle of theta is going to be the same as the angle, or not the angle, but the value of r. So what do you think is going to happen when we draw this out? It's going to be a spiral. And the spiral grows really big, so you may not see the whole thing on your calculators, but if you zoom out enough or if you adjust your spiral, you might see it a little bit better. So if we, for example, if we just multiply this by 0.5 or something like that, we see the spiral not growing as fast or whatever. So anything that has to do with a polynomial would have this sort of effect. And so if I have theta, let's say, minus theta squared, it's kind of hard to see, but it hits 0 at some point, and then it goes negative at another point, and then positive. So we change these things. Change the limits to minus 20 to 20. You might see a little bit more. No, we don't get to see too much more. I suppose you can think about it as a fractal because it looks like it takes on the same shape over time. Looks kind of cool, huh? Suppose it could. Anyways, you could play around with these things, make some nice pictures and print them out on nice paper and hang it in your walls and decorate your bathroom. So we took a look at families of these curves, and I want you to be comfortable with a handful of them, like the regular cosine and sine thetas, and so circles and all the other types of shapes that you might run into. So now let's relate this to parametric equations and see if we can do some calculus on them. So here is the relationship between polar coordinates and parametric equations. So the deal is, I guess this should be f here. If you have a polar coordinate function as a function of theta, r is equal to some function of theta, then if you revert back to the relationship between polar and Cartesian coordinates, where we say r is equal to, or x is equal to r cosine theta and y is equal to r sine theta, we can break this up into the pair of equations that would make up a parametric equation. But instead of r, since r is equal to f of theta, we can just replace that. So if we attach the function to the cosine and set that equal to x, we attach the function to the sine, set that equal to the y, then it seems like we would have a parametric equation that would draw out maybe hopefully the same polar coordinate equation that we had. So, for example, this is example number 1. If r is equal to 1, we know what that is, right? That is your circle of radius 1. That's your unit circle being drawn in counterclockwise direction from 0 to 2 pi. And so if we do this rule and transform this polar coordinate equation into a set of parametric equations, then we would have x is equal to 1 times cosine theta and y is equal to 1 times sine theta. And then we have the circle that we all looked at the very beginning when we started talking about parametric equations. Okay? Yes?
So would the polar coordinates draw out the same function as if it were to be
Yes, it would draw the exact same function. So parametric equations, you usually want to include your limits for your independent variable t. And instead of t, we're calling it theta, or instead of theta, we're calling it t. But if we let that independent variable go from 0 to 2 pi, it's going to draw exactly what this original polar coordinate function is drawing out. So if we want, we can do the same for this as another example. We have r is equal to theta, and so if we take a look at x is equal to theta times cosine theta and y equal to theta times sine theta, we should get that same spiral that we would have gotten. Okay? So I don't know if it's a big deal to you. Usually we refer to parametric equations with a parameter t, but t is really just a parameter, a dummy variable, so you can call it whatever you want. So whether you call it t or theta, it shouldn't matter. What does matter is that if you're using a computer program, it may want you to specify exactly what letter to use as your independent variable. Okay? So as in this example that I'm about to do using my graphing calculator program. So I'm going to go back to this graph. And do a regular graph. And go from 0 to 2 pi. So that I'm looking at this graph. Now, if I want to compare this with a parametric equation, my program tells me that I need to use t for the parametric equation. So as I set up my parametric equation, I'll remember to use t. So instead of theta, I'll use t, and then I have to remember multiply it by the cosine of theta, or cosine of t, and then I'll do the same for the y value. Suppose you can't see that unless we take this out. Oh, I only have a piece of it because my t only went from 0 to 1, so let me go all the way up to 2 pi. And so whether you're looking at that's hard to see. I'll put blue. So whether you're looking at this spiral that's being drawn using parametric equation or using this drawn in red using the polar coordinate function, it's the same thing. It's right on top of each other, so you can't really distinguish. Wish we could make one dotted or something. But it's drawing out the same thing, so you can't see them on top of each other. but that just means they're exactly the same. So that's how we would deal with, if you wanted to make a polar coordinate into a parametric equation for some reason, this is how you would do it. Okay? So, oh, there's other parametric equations I wanted to show you guys, and polar coordinate functions I wanted to show you. I forgot. Let's see. This is kind of a little backtracking and a little bit off topic. Secant theta. So secant theta looks like it's a line. X equals 1. How do you think that happened? Any ideas? Any idea?
X is cosine theta. Or X is our cosine theta. R is secant theta times cosine theta is 1.
So we're saying that if we take secant theta and write it as, what is it? It's the reciprocal of cosine. And then we can just do some simple algebra, multiply by cosine on both sides. And you know that our cosine theta is equal to x, so this is just x is equal to 1. And that's that graph right there. Okay? So you would guess similarly, if you had r is equal to cosecant theta, that this would yield the same thing. And so if we do that, set this equal to 1 over sine, r sine theta is equal to 1. And so that's y is equal to 1. So you'll get some of these problems where you might be forced to use polar coordinates when you're trying to draw a line, horizontal or vertical line, and this is how we would draw a horizontal and vertical line. And so just imagine how that's being drawn. I guess if you're using your calculator, your graphing calculator, your TI-83 or 84, and you have that tracer, you can see how that's being drawn. So I won't go through that, but you should think about it. So that's a little aside that we had to take because I forgot to mention those things. So we were actually talking about making that relationship between polar coordinates and parametric equations, and we have this now new relationship between polar coordinates and parametric equations, and so we could do calculus on it like we've done before, since we've done calculus on parametric equations. So let's type this up. So let's first start by finding derivative, and the derivative again is dy dx that we're talking about. So dy dx, and we're starting off with polar coordinate function r is equal to f of theta, and so if we're going to treat this like if it was a parametric equation, or if we can look at it as a parametric equation, then we can find dy dx like we've done before. And what was it before? It's like dy dt or something, right? But we have to transform this r is equal to f of theta as a function of x and y, or not a function of x and y, but x is a function of t and y is a function of t. So that connection here, which is what we just talked about, is f of t cosine t for the x, and for the y is f of t sine t. And so if we just treat those as your x and your y coordinate functions, we can just take the derivative, take the derivative of them with respect to t. And so we can do that. Take the derivative of y with respect to t is a product rule. So derivative of the first times the second plus the first times the derivative of the second. All right, so that's your numerator, that's dy dt, and then your denominator is dx dt, which is the derivative of x. Derivative of the first times the second plus the first times the derivative of the second, which is negative sign, and so we'll have a negative in the denominator. And this is your slope, essentially, at a particular t value or theta value, if you want to think about it as theta. So you want to think about it as t becoming theta, and then you let theta equal to a particular number, then you're going to get your slope. Right? So let's look at an interesting, one of those interesting graphs that we had, the cardioid. Let's take a look at, not the cardioid, but the limaçon, the one with the hole in it. So let's say r, remember what that was? Like 3 or something minus 2 sine or cosine? Let's do sine t. Kind of picked this one because it's kind of interesting. Do you remember how the graph looks like? Let's see. Let's take a look at the graph. I think, I'm not sure, but I think it went like this. Remember that? That's 2 minus 3 sine. You guys taking notes in pen? All right. So there's a few interesting points to look at. One can ask, since you're looking at the slope, one can ask where the slope of the tangent line might be vertical or horizontal. So there's a couple of places to kind of look at. And so let's try to address that particular question. Where are the slopes vertical and where are the slopes horizontal? What? The graph? Oh, well, yeah, this isn't one of those. It's not being generated by rolling circles. This is a limaçon. Well, there's a lot of those that we can define. That's another family of curve that you can look at. There's asteroids and...
I thought the cardioid was epicyclic.
No. Those are things where you roll this circle and you follow a point and then you get one of these things. And so
No, the circle rolling on another circle.
well, it's essentially the same thing, except instead of a straight line, you're in a circle. But this is not one of those. But you can certainly explore one of those things by looking at, in fact, we might look at that when we start studying vector-valued functions. It's like a rotation of, imagine the sun being in the center and the Earth going around in a circle, and then the moon going around the Earth. And so how's that graph going to look like? So think about that as an exercise that we'll eventually do when we start dealing with more vector value functions. Anyways, we're back to this where the slope's horizontal. So horizontal means the slope is equal to 0 or undefined. It's equal to 0. So the slope's equal to 0 when the numerator is equal to 0, and hopefully the denominator is not equal to 0. So we're interested in finding out the numerator and denominator of this thing. So let's find our derivative, and we could do that as, well, just put dy dx equals. And then we'll deal with the numerator and denominator separately for each of these problems that we're addressing. So we have f is essentially r, so we're going to treat this like this is f of t. I guess, I'm sorry, this should have been theta. And so we're going to find the derivative of this and multiply it by sine, take that exact same function, multiply it by cosine, so that's the numerator. So the derivative of sine is cosine, the 2's gone, so this is negative 3 cosine theta. So that's f prime of t. We'll tack on a sine t there. And then the f of t, without taking the derivative, I'm sorry, I'm mixing up my t's and thetas here. Let's consistently use theta since we are dealing with polar coordinates. And cosine theta. So that's my numerator, and my denominator is down here. I need to take the derivative. Hey, I got the derivative already. It's this one. And then this time I'm going to first multiply by cosine theta, and then the original function sine theta. So to answer the first question, where are the slopes horizontal, we're going to take the numerator. Missed one. Oh, yeah. Well, we'll find it. So let's horizontal. Let's answer this question by taking the numerator and setting it equal to 0. So as I do that, I'm going to see if I can simplify a little bit along the way. So the numerator is going to be negative 3 cosine theta sine theta plus 2 cosine theta yeah. Oh yeah, I think it is. Thanks. All right, where were we? We were looking for this. So that's 3 sine theta cosine theta. And we got two like terms here that we can combine. Fortunately, they don't cancel, but they do combine, so that's negative 6. Is in common? Yeah, so why don't we do that too? So I got negative 6, and then there's a 2 cosine theta, and so there's a 2 cosine theta in there. So let's take out a 2 cosine theta. And this would be 1, and then we took out a minus 2 from the 6. Oh, we took out a 2 from the negative 6, so that's 3. And then this took out a cosine theta as well. Hopefully that's right. Does that look right? And then now we're just going to set each of these equal to 0, because we're setting the whole thing equal to 0. And we want to know where cosine theta is equal to 0 and sine theta is equal to, I guess, 1/3. Is there a square root or just 1/3? I think it's just 1/3, right? What? Are we on the right track? All right. So cosine theta is equal to 0 at pi over 2, 3 pi over 2. This whole thing is done between 0 and 2 pi, so we don't need to go look beyond past that. So let's just say pi over 2 and 3 pi over 2 are our interested values. Interesting values. And sine, I don't know if this is an actual easy number to look at, so what should we do about this one? Should we just, what? I'll just take the sine inverse. So theta equals sine inverse of 1/3. So did your trig teacher tell you that when you take the sine inverse of things, you may not get all the values that you want or you need? Right? So we'll just keep an eye on that and watch out, and we'll use our graph to help us coax some more solutions out of this instead of just relying on what it says on the calculator, the sine inverse of 1/3. Okay. So I can see by the graph that when theta is equal to pi over 2, it looks like I'm down here. And when theta is equal to 3 pi over 2, I'm down all the way at the bottom. So that's pretty clear that those are the two values. When this cosine theta is equal to 0, that's going to give me a 0 slope. Now, the other two over here, these angles must be the angle of sine inverse of pi over 3. Now, if you use your calculator, right, use your calculator and find the sine inverse of pi over 3, then you would get whatever it is you get, the decimal. Yeah, but we're not going to do verticals. I'll let you guys do the vertical ones if you want. But this is the one angle that we're looking for. This must be, if you were to use your calculator, the sine gives you solutions in the first and fourth quadrant, I think, for your inverse, right? So what angle did you get? Let's go radians here. So in radians, 0.3398 gives us the angle where we have that other horizontal line, right? And so how are we going to find this angle? How well do you remember your trig? Pi minus that. So this is pi over here minus, let's say theta is equal to pi minus this angle that we found, which is approximately 0.3398. And that will give us your second angle that we wouldn't have found using the calculator. And it would be good to have a picture so that you can see what it is you're looking for. So I think we found the four angles, the four places where this would have a horizontal slope. Okay? Any questions? All right, let's move on. So the next calculus thing to do is to find the arc length. I don't know if that's the next one, but that's the next one we're going to do. So it'd be interesting to find the arc length of a spiral, for example. And what we're going to do is, again, rely on the fact that we have found a relationship between polar coordinates and parametric equations because we have a formula for finding the arc length using parametric equations, right? So that's our idea, our key here, is to get your polar coordinate function into parametric equations and then use the formula to find the arc length in parametric equations. So whether you look at, again, whether you look at this thing in t's or thetas, it still should work out the same way because, again, they're just dummy variables. Now, if we just kind of go through the process, instead of doing this process all the time, this actually holds a special formula. You know, when we take the derivative of x of t and y of t, which is what we did the page before, we got something that looked kind of complicated, but we're going to have a collection of sines and cosines. And furthermore, we're going to square those things. And so somewhere along the line, we're going to have a bunch of sine squares and cosine squares floating around. So if you want to have some algebra fun with that, you can go ahead and square this, or take the derivative, square it, and then add it together and see how those things would cancel out. Okay? Since I don't want to have fun, I just would rather copy the formula, and the formula is going to be, I hope it's here. So when all's said and done with all those sines and cosines, this is what you're going to end up with. It's just going to end up to be the square root of the function, the derivative of the function squared plus the original function squared. And then you're going to take it from a to b, whatever a to b is. So for an example that we're not going to do, but if you let r is equal to 5, and then say you want to go from a is equal to, oh, I don't know, like pi over 6, and b is equal to like 2 pi over 3 or something like that, and then do this integral with f of theta equal to 5, then what would you get? You'd get the answer for number 1 in your warm-up. Okay? Yeah?
Does this also rely on an x being equal to 1?
No. Well, x is going to be 1 to 1 for this case. When we look at this function, x is going to be 1 to 1. Wait a minute. No, you don't need 1 to 1 for this. Do you? No. What do you need 1 to 1 for? When did we have that? Was it arc length or was it something else? No, I don't think you need it for arc length. You need it for something else. Area under the curve, area under the curve. So for arc length, you don't need it. All right, so let's do an example. Let's say, oh, you know what? The one that we were doing, the cardioid, no, the limaçon. Let's take a look at that. But just to make things a little bit more interesting, let's find the length of not the whole thing, but just that little loop. Remember that this is a C with a little tail in the bottom, not a G. Kind of looks like a G. So this is an interesting problem because we're a little bit we need to do a little bit of legwork to figure out something else before we just throw this into an integral. I mean, the integral itself, I think, you know, the integrand itself would be easy enough to find. What was this again? 2 minus 3 or 3 minus 2? 2 minus 3 sine theta. So, like I said, the integrand is going to be clear. We just need to take the derivative and then do all that stuff. So r prime is equal to minus 3 cosine theta. And so I think to set this integral up, we're going to have minus 3 cosine theta, and go ahead and square that, plus, and then we have 2 minus 3 sine theta that we have to square d theta. So the hard part, what's the hard part? Well, what else is missing? A and B, we need to find the limits, right? Limits of integration. So, how are we going to find the limits of integration? Well, what's happening? Where? What? Who? What? We just want this little bit, and this little bit will have a starting point and ending point. So how are we going to find that? Yeah?
We can split it up into, like, if we find the y value there, we can just multiply. If we're finding the part, then we can just multiply it by 2, finding from that top point there to the line.
So you're saying maybe we can just look for this part?
Yeah, look for that part and multiply it by 2.
All right, I'm game for that. But it's still a little bit of an issue because I still don't know what those things are. No? How do you think we'll do that? How do you think we can find the theta values that would draw out this little bit of our graph? Set r equals 0. Why would you set r equals 0?
Because both the start and the end are the only 2 points where r equals 0.
Well, the start. What do you mean by start? Because we started over here, I think.
The start and end of the integration. The part that we want to integrate.
Well, the graph is r, yeah?
Well, yesterday you said the hole was caused by the dip underneath the x-axis.
So if you graph this out,
Yeah.
you can see, so when, David? Yeah, so Dave, so when you were explaining this, you were saying, why did you say 0 again? So Caroline made sense, but
Yeah, well, I mean, the loop, again, it's where the radius is 0, the starting and
yeah. So the r, remember, is the radial distance from the origin. And if you were at the origin, this is where you want to start, then you want your, essentially your r to be 0. And if you looked at the graph over here, then you'll also see that same effect. That's when your y value, or if you want to look at this as your r value equal to 0, then that's exactly what's happening. So we're going to set r equal to 0. And that'll give us one of these. And if we only go halfway, Do you remember what this point was that stops over here? You know what that angle was? Pi over 2. So if you remember this being drawn, by the time we get to pi over 2, this is drawing on the opposite side, right? Wait, these r's are going to be negative. Is that going to be an issue? I don't think so, because we're going to square it anyways, right? Okay, so we know that we're going to end at pi over 2. And trying to figure this out, we'll just solve for r equal to 0. So let's solve for r equal to 0. 2/3 sine theta equal to 0. So what is this? Sine theta equals 2/3 or 3/2? 2/3. So again, the arc sine is going to give us, going to help us find its value. So whatever this, can somebody punch this in their calculator and give us an approximation? And we're in the first quadrant, right? This happens in the first quadrant. This happens somewhere here. That's when it comes down to 0. So did anybody get this approximately? Can we have a check on that? Concur? Yes? What?
What was the value that we solved for alpha? I thought that was that number as well. The 3398.
That's a sine inverse of 1/3?
But where is it on the graph?
Right here. It's clearly less than what's pi over 2 is like 1.5 or something, 1.57, and 1 would be somewhere over here, so it's less than 1. So I think we're good. And here, 0.79. So that also looks like it's a fair, it's a reasonable value. 729. Okay. So I'm not going to do the integral, but just to absolutely make sure, well, not absolutely, but just to make sure that we're getting this right, I'm going to draw this going from, what is it, 0.729 to pi over 2. So it is, in fact, that little bit that we got, we started from 0 here and we went to whatever this is, pi over 2. Okay? All right, so that's good. I was looking at that clock over there and thinking, oh, I'm out of time. I guess we could take a look at my clock, which is saying that I have more time. All right. So I'm still not going to do this integral, but if I just put a box around here and say this is, either work it out by hand if you want some good practice on integrating things, or you can, it's actually more of a trig problem because you want to simplify this so that you can try to integrate it. Or you could just punch it in the calculator. You guys are all experts in finding integrals in your calculators now and getting numeric values. Or you can punch it into Wolfram alpha. Okay. So that's the arc length. Any questions? So the difficult part about this problem was trying to figure out what the limits are for your integrals. And I think that should be the hardest part in any of the problems that you guys will be doing, because otherwise it's just plugging and chugging, right? Just you got the formula, you got a function, you look for the function, you take derivatives and plug it into the formula, and that's all you really need to do. Yeah.
On the test, will we have to
Are you talking about calculating the integral?
Yeah.
In the test, a lot of times I'm not going to ask you to calculate the integral. I'm just going to have you set up the integral. I may ask for the calculations, which is why I wanted you guys to be able to be comfortable to use your calculators. But, you know, finding integrals and stuff like that was stuff that you did in Calc 2. And I'm not teaching you Calc 2. So I'm assuming you know Calc 2. And I think to gain more intuition on these polar coordinate graphs, I think the best thing to do is to have your calculator, plug in one type of function, change a parameter, and see what happens. Okay. Do that. It'll be easier and funner, too, because you'll see colors and stuff like that instead of just your graphing calculator. It's not so portable. Like, you can't, I suppose you can take the computer in the bathroom and plug this out. Whoa. All right, the last thing we want to do is the area, but instead of having the area under the curve, this is Harrison comment about being one-to-one. When we did parametric equations and finding the areas under the curve, we found the area from the parametric curve to the x-axis. Okay. Now, with polar coordinates, there's something that's a little bit more natural than finding the area from the curve to the x-axis. And that is to find the area from the curve to the origin. And so it spans out something. And so for that, you need a special formula, and that's the area of a sector of a circle. So I'm skipping the idea of the derivation of this formula, but just to give you a little sketch and a little preview if you want to look at it in your book. The idea is that you have a curve r is equal to f of theta going from some angles theta 1 to, I guess they call it A and B, so we'll call it A and B. And then you're looking for this area. So you're looking like a piece of pie if this was a perfect circle. If it's not a circle, then it's, you know, it's not a circle pie, but well, I don't know. You can make up your own analogy with pies. Oh, not 3.14, but an actual apple pie. All right, now I just got confused. So the idea is to break this up into little subsectors, and that's how, you know, you're finding the area under the curve. You break this up to little rectangles, and then you add up an infinite number of rectangles and stuff like that. So.
I remember doing something similar. I remember someone did something similar in chapter 3 back when we were finding the area, or finding the volume of a cylinder. It involved something similar where you sort of, when you find it for the base, where you sort of broke it into triangles, and then but that I remember that not working.
Okay, well, that's not what we're going to do.
It's just that I kind of see this similar. I don't see what's the difference.
No, we'll could talk about it after class. So here is our sector. If we break this up into little subsectors, a bunch of little subsectors where the angle between those little subsectors would be like delta theta, then looking at this as r is equal to f of theta, and instead of the angle theta, we're going to call it delta theta, since that's the little space between those two angles, theta 1, theta 2, or in this case, theta sub I 1 or whatever. then this is just the 1/2, and this is your r squared, your r squared being f of theta, and then your theta becomes delta theta because we're looking at little subsectors. And so if we imagine adding up an infinite number of these and put it through the Riemann sum business, then you're going to get this integral. So that's the general idea behind this formula. Again, I'm being general about it. I'm not being exact or precise. And if you want the exact or precise proof, you can look at your textbook. But now that we have a formula, we can easily apply this by doing, finding areas of stuff. So, for example, if we want to find the area of R equals, what is it again? 2 minus 3? And we'll go with that little loop again in there. And we want to find the area of that little loop in that limaçon. Then we just plug it into the formula. Now that we have the formula, it's not derived. We just plug it in there, and then we should get our value. We can do that approach also, or we could just double it, right? If we just, since we did it from the previous problem. So the area is going to be, let's double it, and instead of going from whatever the angles are, let's go from the angles that we went last time, which is, what is it, 0.729 to about pi over 2. And then the formula says we need a 1/2 out in front. Because we're going to just find the area of half of it. So this little part is just going to get half of it. And then we'll just multiply it by 2. That doesn't look like half, does it? That'll work. All right, so the function is the function 2 minus 3 sine theta. We'll close that up and square it, and just d theta, and then we'll be all set. If we'd found that other intersection, which would have given us another numerical value, then we could have changed. Instead of doubling it, we just go from that to that. I think so. Yeah. So, should we find the value? Should we punch it in the calculator? Nah, you guys can figure it out. Okay. Any questions? Yes. Oh, because this business over here, since we took the limits from where it hit 0 and where it went down here, and we didn't bother going all the way up around to the other side, since we're essentially looking for half of this area, and so we're just going to double it. And that's another thing that you'll see is that when we start doing a lot of these things, especially when we start doing polar coordinates and then we start doing surfaces in 3 dimensions, we're going to try to take advantage of as much of these things as possible where we're going to use symmetry. If it's symmetric about something, we're going to tend to say we're going to double it instead of finding the whole thing. We're just going to find half of it and double it. So you might want to integrate over a sphere, for example. Now, instead of looking at the whole sphere, maybe we might just be interested in taking half of the sphere and then doubling it. So take the top half of the sphere, integrate it on that, and then double it to compensate for the bottom half. But you have to make sure that it's symmetric to be able to do that. And to do that, you need to be able to visualize. You need the graph of this. You need symmetry on the equations and stuff. Okay, so that is that? Conic sections. Oh, we have 5 minutes. We should punch it in our calculators and see. Or maybe we can do a problem from homework. Oh, the math autobiography? To be continued. That's pretty lame. Oh, this is all being recorded. This is recording me stealing homework from another class.
You know, it's one example of academic integrity.
Yeah, I know. What if I say it's borrowing? Then is it okay? So the math autobiography is basically your math background. I used to do this for all my classes, and then I kind of stopped assigning this to Calculus 3 students, and then I thought, well, why not? Because I think, one, you guys should be able to write paragraphs and stuff like that. I know it's a math class, but I think it's important to be able to write. And then two, it'd be interesting to know a little bit about your background in math. Now, I'm assuming that you're in Calculus 3, that you have a fairly strong background in math. But I'd be interested and sometimes in reading some of these, I can kind of gauge your confidence in math. Sometimes I can't, but if you're feeling a little nervous about this because you haven't taken math in a while, or you're feeling a little nervous about this because you barely passed Calc 1 and 2, then those are the type of things you want to be able to express and write about, so that I can kind of see where you're coming from. And, you know, like I said, somebody asked about having to compute these integrals in the exam situation or quiz situation. And in general, I don't really care if you're able to compute integrals. Because an integral computation is something that you can just punch into the calculator or computer. But on the other hand, I think there is some value to being able to integrate these things. So what I try to do is I try to make it so that it doesn't, you're possibly getting a C in Calc 2 isn't going to hinder you too much in being successful in this class. As long as you can understand the concepts that's being introduced in this class, I'm good with that. I mean, there's some things like taking derivatives is just, that's important, and you have to be able to take derivatives. But computing integrals, especially these nasty integrals that we're coming up with, you know, trying to do that by hand could be close to impossible. It might be impossible for some of them, so it's not productive for us to spend too much time on calculating those things. So these are some of the things that I would be interested in having you put into your math autobiographies. No more than 2 pages, because I'm reading a lot of them, and but I want you to spend a little bit more than half a page on it to kind of look to yourself to see how you are as a math learner. So that's what this is about. Okay, how you guys doing on the homework? I think the first one is due on the 28th.
First two of them are due.
First 2, yeah, there's 2 of them due.
The next two are due on the 30th.
And then the labs, yeah, the labs are due also. So I'd encourage you to really take a look at those labs. The labs are, you know, they're in the same order as the homework. All right? Yeah, it's all under assignments.
Oh, that's what that is.
Yeah. All right. Good luck. Go get them.